So for this video, I want to answer the question, why do we have airbags in cars? And to answer that question, we need to understand two different physical quantities. The first one is momentum. That is represented with a p, lowercase p, and it is a vector, and it's the product of the mass and the velocity of the object. So something that isn't moving has no momentum. Anything that's moving has momentum, but we're only going to cover masses that are moving in this class. The other, well, before I move on, always check the units. Kilograms, meters per second. The other quantity we need to understand is called impulse. Impulse is represented with a capital J, and it's the product of the force and the time the force is applied for. So it's represented with, or sorry, the units for it are the Newton seconds. And the reason why we need these two has a lot to do with second law. And second law states, or at least the second law is the way we know it, states the net force is equal to the mass times the acceleration. But I write it as the acceleration is proportional to the net force, inversely proportional to the mass. That's not really how Newton wrote second law. What Newton said was that the force would create a change in momentum or for like a given time. And if you notice here, if we multiply both sides by that time period, we basically get that the impulse creates a change in momentum. And we can expand this a bit further. So if the mass is consistent, the force that we apply to it will change the momentum, but if the mass stays the same, the velocity is what's changing. And we can work backwards from there. So let me change this up here. And we can see how Newton's second law relates to this impulse as a change in momentum. We call this impulse momentum theorem. Or how I originally had it. And hopefully this is not too foreign of a concept. Remember, we said work, where the net work created a change in kinetic energy. So in this case, a net impulse will create a change in momentum. Except this was force for a parallel distance. So that's impulse momentum theorem. And what does this have to do with airbags? Well, consider two scenarios. You are in a car and you slam on the brakes. So you got your steering wheel and dashboard. You are flung forward. In the second scenario, you're flung forward, coming to that stop, but the airbag has deployed. In either case, your change in momentum is going to be the same. You're going from, so let's say we're going from some speed, from v to 0. So our final momentum in both cases will be 0, and our initial momentum will be mv. So change in momentum for both instances will be negative mv. So according to impulse momentum theorem, that change in momentum is going to be is going to require the same impulse. So if our impulse is locked in, what's the point of the airbag if this isn't going to change? Well, in this instance, the airbag, or without the airbag, you're going to be brought to a halt pretty quickly. With the airbag, it's going to compress, and it's going to take time, even if it's just a few milliseconds, to compress. So in one instance, we have an awful lot of time. Another instance, we have a small amount of time. Well, to produce the same impulse, that means an average force is smaller that's applied to you in the airbag situation than the average force that's applied to you in the dashboard situation. So when it comes to the two quantities, it's the force that we worry about when, as far as our safety. So we want to increase the time it takes to stop. So consider a force time graph for both scenarios. So we'll say this is the dashboard and this is the airbag. Well, for the dashboard, we have a small amount of time to bring you to a stop. So we said large force. For the airbag, we have a slightly larger time, and we'll have less force. Well, hopefully you can see what should be equal here. Anytime we see like multiplication going on, that probably indicates to us that we're looking at the area. Consider a constant force applied for a time. That would be the base and the height. So the two areas here are going to be the same. It's just as far as safety is concerned, we prefer less height, more base. Okay, now, so hopefully I've answered the question of why we use airbags in cars, but I want to talk about why we're taught to follow through in certain sports like golf, tennis, baseball, anytime when we're asked to hit something. So imagine you have a golf club and you hit the ball, but you don't follow through. So you kind of stop your swing and the ball has left. So that's scenario 1. In scenario 2, you're still swinging just as hard as you can. So the force you're applying, so the force being applied to the ball is still the same the whole time. But this time you follow through with your swing. So what's going to happen to the time that you're in contact with the ball? So if you're swinging for longer, or if you're following through, for the same force, that means we get a larger impulse. So this will be no follow through. Here we follow through, and let me redo this one. So short time, same amount of force, so we apply the ball at the same time, but we follow through. And you'll see we get more impulse here, more change in momentum because of the follow through. So to compare the two instances, the force is locked in. We're swinging as hard as we can. It's just one, we're applying the force for a short time, the other one for a large time.